welcome everyone. This is the first half of the session. My name is Paul. I'm very happy to be chairing the afternoon session. Our first speaker is our second tutorial today. Panagiotopoulos will tell us about homological invariants. Please, if there are any questions during this talk, feel free to just interrupt. Also, I'll be monitoring the Zoom meeting, so if you have some questions online, just put in the chat and I'll interrupt Aris and ask a question. So go ahead.
Yeah, hi there. It's nice to see your new faces because I don't know anyone. So yeah, and feel free to interrupt at any time. This is a tutorial, so it should be. I'll try to communicate in terms that hopefully everyone can understand. But if there's something that you want to stop me and ask me to explain, feel free to do so. Right. So this is about an ongoing research program. All three lectures will be about that. So this is an ongoing research program that is joint work with Jeff Bertholk and Martino Lupini. Last time I saw Lupini, he was in New Zealand. Now I'm not sure what he is. I think he's in Newcastle in the UK. And Jeff was in Vienna. I think now he is in a sabbatical in Barcelona. So there is already a paper on the archive, and it has been there like for some time. But we were hoping to finish the second part of this work to try to have them out together. So sometime in the next month, the second part of the work will come out, and then we'll try to see where we can send them. Right. So what's the goal of this program, right? So the idea is this: often a lot of invariants in algebraic topology and homological algebra are treated as discrete objects. You know, you have the let's say Steinert homology is a certain homology theory, right? And what a homology theory does, you feed it topological spaces, let's say compact topological spaces, and these compact topological spaces adopt some group, meaning the homology of a topological space becomes a certain group, abstract group. Usually we treat it as an abstract object, abstract group. And then hopefully, when you have two topological spaces that are very different, hopefully the associated groups will be very different. And so you'll be able to say that these topological spaces are not the same, are not homeomorphic, because you just check that these invariants, these algebraic invariants, and you witness that these groups are not isomorphic, right? So, but this usually the way we treat these groups, the groups that we get from Steinert homology or from Chekhov homology. Chekhov homology is another sort of invariant. You feed it, let's say, locally compact topological spaces, and the result is some sort of group. In fact, has additional structure, but it's an algebraic structure usually. Similarly, in algebra, let's say you can have a pair of abelian groups, and you can feed them inside this X functor, and this gives you a certain invariant that captures something about this pair. I don't want to go into detail about that. Similarly, there's another functor here that we feed it certain inverse systems of abelian groups with homomorphisms, and this invariant remembers something about the system. It's not very important. It's not very important for this talk to know what these things are. All of these things can be obtained as homology or cohomology groups associated to a certain chain or cochain complex. This is what we're going to see in the next slide. But before I go there, the point is that what we do is that we take these abstract groups that are the results of applying these functors, and we add some additional structure that makes these invariants much finer. If before you couldn't distinguish between two spaces that were different, let's say you have two spaces that are different, but when you compute the homology, it turns out that the homology, that these groups are isomorphic. Somehow maybe the homology couldn't really see between the differences very well. Well, now what we do is that we have we add some structure on this, and we come up with finer invariants, the definable homology, and this definable invariants carry some additional structure that hopefully will allow you to distinguish between objects that you couldn't distinguish before. Right. Okay. So let me repeat what I said before. That all the invariants that I presented before, all this, there's a uniform recipe, if you want, for how to define them. What you do usually is that you start with, so let's say in the first case, when we were talking about theory of homology, objects there were topological spaces, compact topological spaces, and for every object, you associated the homology group. How do you do that? Well, what you do is this: you start with first you start with, let's say, an object, and let me instead of repeating myself and telling you what you do in homology theories and cohomology theories, let me just fix. I'll be talking about cohomology theories. In fact, the second homology, the X and the lim1, all these three things come from co-chain complexes, as I'm going to explain later on. So this is the only one that instead of a co-chain complex, you need a chain complex. So let me formalize everything and discuss everything in the context of co-chain complexes, right? So one starts with the collection of objects that you want to classify, and for every object, in order to compute the homology or the cohomology in this particular case, you first have to associate with the object X a certain cochain complex. So what is a cochain complex? A cochain complex is a sequence like this, where like the nth term here, collects all the pertinent n-dimensional data, pertinent for the problem that you're trying to, you're trying to understand the objects from a certain perspective. So there you record all n-dimensional data that you care about, and you turn them into a certain abelian group, right? And the morphisms are just, which are called co-boundary maps. They go upwards because this is the co here. What co means that the morphisms go upwards. These are group homomorphisms. That's the group homomorphisms. And once you have this situation, you can extract the n-dimensional homology group associated to the object. So what you do is that you have to look at this triad here. Let's say if you want the n-dimensional homology, you have to center the picture around the nth coordinate here. So you have a map that comes in and a map that comes out, right? So you look at the kernel of this map. This will be a subgroup of this, and then you divide it by the image of this map, right? So you have a group which is the kernel, and then inside it there is a subgroup, and you divide the bigger group with a smaller group. The fact that the image of delta n sits inside the kernel of delta n plus 1 is the same as saying that this is a cochain complex. A complex means that it's a central condition. That's that if you compose two consecutive maps, you get 0. Right? So you get this abelian group, and depending on what data you recorded using this cochain complex, this associated cohomology theory you can use it for different reasons, right? So now the thing, and this is like the important point here, is that in many classical homology or cohomology theories, it turns out that these abelian groups carry with them some additional structure, some topological structure. Actually, often these are naturally topological groups, as a matter of fact, right? And nowadays, so one would hope that maybe out of this topology you can add some structure here, right? So this is, if I'm to cite here Dieudonné from the book A History of Algebraic Topology, Expressive Topology, in the beginning of the previous century, there was a trend until the 1950s, but this trend was later abandoned. And what was this trend? Is to consider the general homology and cohomology groups as topological groups for suitably chosen topologies. Well, what suitably chosen topologies here usually means is the following. Usually this same complex here, the objects here, carry a natural topology that comes from X, and therefore this group and this group, both of them are subgroups of this. So they have the subspace topology, and then you can put here the quotient topology. This is something you could do. So instead of thinking of them abstractly, why don't we think of them as topological groups? Well, there is a good reason as to why this was later abandoned, and the reason is this. Often what happens in interesting situations, the image sits densely inside the kernel. And so the topology you get is trivial. It's just the empty set and the entire thing. So where you would hope that maybe the topology will give you something more interesting, it turns out that the topology is trivial and doesn't give you anything interesting, right? So let me give you an example for that, right? So let me, I will not do the computation, of course, but just to give you some information about, this is a very important example, historical example, right? So what's the two solenoid? What we do here is that T for me is that the circle is, right, it's a circle, and you take two copies of the circle and you wrap this twice around that. And you keep doing that, and you're taking an inverse limit. Now, of course, you can define inverse limits entirely in abstract terms, right? But you can also think of them a bit geometrically. And just because it's nice to have some pictures, let's do that. Let's try to see how the inverse limit would look like, right? So here you can see. So to think of it geometrically, what you have to do is you have to take these circles and turn them into solid tori, right? So here you see the outside solid tori, torus. And the second coordinate here is the funny thing that's wrapped around twice, right? But now that you have the second thing that's wrapped around twice, the third circle, which will correspond to some sort of new solid torus, it's going to wrap around the green thing twice. Well, 4 times around the yellow thing, right? So you start with the first coordinate. When you go to the second coordinate, you have that. Then you have that. It keeps going like that. When you take the intersection of all this, what you get is the two solenoid. Now, a fact that I'm going to just throw here, you don't need to know how to compute that. I haven't even given you what's the definition of the standard homology. But one thing maybe it's interesting here because it's an important example historically, is that when if I tell you what's the definition of the standard homology and you spend a lot of time, you'll figure out at the end that if you look at the zero dimensional group, let me say something before that. Just to have a little bit of a better understanding of how this looks like. You see, if you take the solenoid and you project it down in a certain sense, you can project it all to a circle. This circle was the original circle, the first circle in the inverse system. Now, if you pick a point in the circle, the pre-image is going to be a copy of the counter space. So you can think of the solenoid here as a circle sitting down, and you take this point above, you have a counter space, and there is as you go around, this keeps being the counter space, but when you go a full loop around, it's attached to the previous copy of the counter space, but in a certain perturbed way. So it entangles. And if you think a little bit about this picture, you'll realize that how many connected components, path components there are uncountably many. This is what it turns out to be. So zero homology, what it usually tells us is that how many connected components space has. Usually this is what it's trying to capture. And here what you get, indeed, is that the connected components are uncountably many, but in a very certain way, right? So if you compute the zero standard homology group, so what you'll get here, you'll get the dyadic integers. So this is this.
So that's not integers mod 2. I was wondering.
Yeah. It's a dyadic integer. So it's an uncountable. It's like the counter space endowed with a certain group structure, right? And the dyadic integers inside they contain the integers, right? But the point here, right? And it turns out that the zero homology group here is this quotient, which we have a continuum mode countable, you get the continuum, right? But the thing is that, as I pointed out, if you keep track of these topologies, here the Z2, the dyadic scale, the usual topology, and Z, which is the integer inside them, sits densely. So because Z sits densely, the quotient topology is trivial. So here you get that you don't get any information if you look at this homology group as a topological group with a quotient topology, right?
I have a question. I know tons of different homology theories. I forget what Steenrod homology is.
Right, so the long answer is that the short answer is that the long answer doesn't matter here, not at all. But the mid answer is that if you remember at all singular homology, which is you look at you start by looking, let's say you look at the interval, you try to map the interval inside your space, and then you think of all these maps as some list of generators, and then you span out an abelian group out of it. Well, synod homology that's something more subtle. It allows you for certain infinite sums of it's like finer. It allows you to talk about infinite chains rather than just finite chains, right? Because in the singular homology, at the end, the chains there will be formal finite sums of images of the interval inside the space. Synod homology allows for infinite sums as long as the sums are controlled and they converge in a certain sense. So it's like a stronger homology, but still it's not strong enough, as we'll see later in this tutorial. Right, that's why we turn it into define the homology and it becomes even stronger, and then we're happy.
Right, one last.
Yeah.
So like if you did the singular homology for this space and did the H0, what would you get?
So here you would get just an uncountable sum of z's, like a continuum size, but with not very specific topological structure. Okay, the structure will be probably the discrete space, maybe. I haven't thought about it.
Okay.
But the fact that the synod homology allows chains that are infinite in a certain controlled sense, this controlled sense makes the topology here interesting. It tells you that somehow when you're trying to figure out what are the connected components, there is some topology going on there, and this topology and some algebra. Right, and this somehow it's good to index it by the dyadic indices somehow. So the synod homology allows you to be more specific. It's not just an uncountable sum of z's; it's something more is going on. All right, so let me go. Okay, so the point here's a concrete example that in a certain homology theory, the synod homology theory, we would like to think of this we would like to exploit the topology. But the topology is not really exploitable. It doesn't allow us to do anything, right? So that's why maybe let me go back to Diodones' quote here. So they were trying to do that, and the example they basically after this example they stopped really caring so much about the topology was the solenoid that I just pointed out before. So after that, and this is how usually we are taught these things. Usually we are taught these things as being abstract. Usually when someone learns homology. Homology theories, usually these are abstract. Now, this is the point of this talk, is that one of this series of lectures is that we would like to have a structure that exploits the topology in an essential way, and this is what this is going to be about, right? So to do that, let me adopt the historical approach here, and let's say that there were two parallel stories in the 50s. So the one is the story that have been narrated so far, right? So this is a story of various folks like Allenberg, Martellane, and Steenrod that were trying to figure out how to classify spaces and various algebraic objects. As a matter of fact, a lot of the interaction between them came because some of them cared about certain algebraic constructions, others cared about certain topological constructions, but then they realized that the objects that they get while they're trying to analyze things are similar objects. So the constructions ought to have something in common. And this is somehow what led gradually to more algebraic techniques and the development of eventually algebraic topology and homological algebra. Right? But there is another trajectory, and this trajectory is a little bit closer to my heart because this I had to learn recently, but that I learned in elementary school, let's say. This is the trajectory of Epros, Glim, and Maki, which led to what we now call invariant descriptive set theory. And this is what we're going to use to refine this invariance here. That is no structure we're going to add. And maybe well, I'm going a bit slow, but it doesn't matter. Maybe what I want to do is I want to spend a few minutes here and discuss a little bit what Epros, Glim, and Maki were trying to do, and how this led to invariant descriptive set theory. So let me see if I can do this. We have to take with us also the people who are on Zoom now. So, all right. So perhaps. So what they wanted to do is they want to understand irreducible representations up to unitary equivalent. They want to classify them, right? So you can fix gamma, let's say for us, is kind of to be a countable discrete group. Do you see it there? Is it okay?
The magic marker is weak and it doesn't at all show through the projector screen, but I can deal with the second one.
Hopefully right below now. So I just start with a countable discrete group, and what I care to say is I want to look at all irreducible representations. So this is in any Hilbert space, right? In any Hilbert space, and you have the collection of these. So you can identify these with certain homomorphisms from gamma to the unitary group of some Hilbert space, right? And for them to be reducible, in a sense, that they need to use the entirety of the Hilbert space in an essential way. I don't want to go into formal definitions, but somehow there's some sort of a density requirement here. You don't, okay. So a representation is irreducible if you cannot split the Hilbert space into two non-trivial subspaces which are invariant under the representation. But so these are the building blocks of all representations, and they wanted to understand the building blocks of this of irreducible representations. So they wanted to. So if I give you two representations, it could be very well that these are the same representations up to unitary equivalence, meaning you can conjugate one to the other using a unitary from the one Hilbert space to the other. So what they wanted to do, they wanted to understand this classification problem, which I will write it like this, and you'll see later on why I write it like this. This is a classification problem for me. That I fix a group gamma, and I want to understand all irreducible representations up to unitary equivalence. And now the theory there, and this theory was being developed at that time, told you that, well, here you can classify if the group gamma is abelian enough, let's say, right? So if you start with if the group gamma is Z, then you know that irreducible representations, well, yeah, irreducible representations have to be one-dimensional. So basically, here the Hilbert space you look at is the complex numbers, and in a sense, it's a representation. You take the circle and you just rotate it. You can rotate it by a rational number, by an irrational number, but you rotate it. So for every point in the circle, you have a rotation that corresponds to irreducible unitary representations of Z. But conversely, every irreducible representation corresponds to a point in the circle, and 2 points which correspond to different rotations by different angle. If the angle is the difference is not a multiple of 2 pi, then the representations are distinct. So basically, you can really classify this. You can really classify this by, well, before I was using the letter T, by the circle. So what I'm saying here is that there is a map from an irreducible representation of Z to the circle, so that 2 irreducible representations are unitary equivalent if they map exactly to the same point in the circle. So basically, you can reduce this pair to the pair circle comma equality. You can classify. You can in a constructive fashion classify irreducible representations up to unitary equivalence using the pair circle comma equality. I'm now trying to get close to invariant discrete set here. So this is when gamma is Z, but if gamma is abelian in general, or it's close to being abelian, similarly the classification is easy. What Efros and Glim realized is that if you are far from being abelian, it can get very nasty. We don't have any concrete way to understand, to classify irreducible representations. For example, for the free group with 2 generators, we still don't know. We don't have any sort of meaningful invariants that allow us to completely classify irreducible representations of the free group up to unitary equivalence. So this is the trajectory. So they were trying, okay, here you put groups that are more complex. Can you classify this? And they were trying to say, basically, the problem of classifying them is too hard. And how do you quantify over this hardness? This is what this question of how you classify over this is how complicated this is. This is what gave birth to invariant distributed set theory. And this is where, okay, so maybe let me now be a little bit more formal and go back to the slides. Right, so, okay, so formally, in invariant distributed field theory, classification problem is just a pair x, e, where x is a polyspace. So a polyspace is just any separable topological space that you can put a metric that is compatible with the topology, and this metric is complete. You can find, so it's any completely memorizable topological space, separable topological space, right? And E is just an equivalence relation of an X. This is what a classification problem means. For example, this is a classification problem because there is a certain natural Polish topology you can put on the space of all in addition to representations. Right? And maybe more combinatorial example, and it's more easy to understand what's going on, is that let's say you are trying to understand the problem of classifying countable groups, countable graphs up to isomorphism. Right? So what do? One way to think of this as a polyspace is to associate a graph with the adjacency matrix. So it's an infinite by infinite matrix of zeros and ones. So maybe you have to impose some restrictions. For example, if your graphs are irreflexive and let's say symmetric, this should be reflected into this matrix, into how if you put the 0 in the k, L, then 0 you have to put on in the L, k coordinate as well. But the point is that you can realize the collection of all graphs, of all countable graphs, as a subspace of the Cantor space. And the Cantor space has a topology. It's a Polish topology, and graphs, and this set is a closed. So this is a closed subset of a polyspace, so it's Polish. So graphs, the collection of all graphs forms a polyspace. And if I give you two graphs there, I'm asking you, do you have an efficient method for telling whether these two things are isomorphic? This problem is a hard problem as well. But once you have this problem, the problem of classifying graphs up to isomorphism, and you have this problem of classifying irreducible representations up to unitary equivalence, you can ask which of the three is more difficult, what is more complex. And the way to address this, at least the solution, what the invariant distributed theory does, is that it provides a framework for asking this question. And this comes in the form of existence of a Borel reduction. Right? So let's say you have two classification problems, xa, ya. A Borel reduction is from E to F, is any Borel map, so X and Y are topological spaces, so they have a certain collection of Borel sets. Now, I like to think of Borel sets as follows. Someone gives you the topology, and now to form the Borel sets, you need to close the topology under countable unions and countable intersections and complements. So basically, if I hand you the topology and you have a computer with countable gates, countable ends, and countable ors, you can compute the entire Borel structure, right? So Borel sets is everything that is computable from the topology. If I give you a machine with countable ends and ors of countable size, right? So okay, so a Borel map is anything that is any map that pre-images of open sets are Borel, or equivalently pre-images of Borel sets are Borel. So this means for us, Borel is a notion of definability. That you any construction that you can perform in analysis by taking limits, or many constructions, maybe not every, but most of them, result to Borel maps. Continuous maps are Borel. But moreover, if you have a map that is a pointwise limit of continuous functions, this function may not be continuous, but it will be Borel. And if you keep closing by pointwise limits, still you stay in the Borel region. So asking for a map to be Borel means it can be described. It can be described basically in a concrete way, right? So okay, so you have two classification problems. A Borel reduction is any constructible map, something that's going to write without the axiom of choice, let's say, a useful map, so that 2 points are E equivalent if and only if the image is F equivalent. So this means the following. It means that, and whenever such a map exists, I will write it like that. This implies that the complexity of this is less than or equal to the complexity of this, because what? If you have an oracle that knows how to classify this problem, then up to Borel reduction, you can classify this problem as well. This is what it tells you. Are we good? So now once you have objects, your objects are these pairs, and you have morphisms, and you study this poset, you can form a whole complexity theory, right? Yeah.
What is this set graph end up? What is this?
This is the collection of, so if you want, this is the collection of all, let's say, how to write this, let me think. You can think of it of infinite by infinite matrices, that each entry is either 0 or 1, right?
Also, it's the end that stands for the number of vertices. It's the graphs on the set of vertices, which is the natural number.
Yes, these are the,
And then when you say graph, I mean this is like a simple graph. So there's either an edge, under
Yeah.
an edge, or not.
There are no loops, there is
Oh, but it's direct.
in my case it's not, but if you want to take it directly, it's fine. Yeah.
Okay.
Yeah, in my case it's not direct.
So
So
that kind of symmetry.
if you put one here, you have to put one here as well.
Uh-huh.
Right? And then here you have 0. Because you don't have loops. Right? But from the perspective of complexity, it doesn't matter. It turns out that out of all sort of discrete, out of all problems, isomorphism problems between canonical structures, the one I'm describing there is the most complex. And this is going to be reflected in my next slide. Right? So this is how the Borel reduction hierarchy looks like. Here in the picture I've drawn, the point is that as you go up, you get more and more complex, right? And here in the beginning, things are linearly ordered. I will define these three things. But in the beginning, it's linearly ordered. You have a certain complexity class here, which is called completely classifiable classification problems. And this is like the least complex. And there is a jump. There is just strictly above, there is one, which is what we call, well, both together, they call them hyperfinite. So every classification problem that reduces to either of these two, we call it hyperfinite. And then there is this cluster here. So from this point and above, something weird happens. Linearity breaks, and Borel reducibility becomes a partial order. So you can have two classification problems that you cannot classify this using this as an oracle, and vice versa. Right? So linearity breaks. And this cluster here, these are all problems that look like graph isomorphism. Well, let me concretely give the definitions. Let me open up so people can read. So you are concretely classifiable if you are reducible to equality, like here. So if gamma is Z, then irreducible representations up to unitary equivalence is concretely classifiable. Right? The next thing, and this is an important, this problem here is an important equivalence relation. So here I look at the Cantor space and I look at E0. This is an equivalence relation, which denotes eventual equality. So these are 2 points in the Cantor space, right? So there are infinite sequences of zeros and ones, and they're eventually equivalent if they're equal from a point on, right? If there is an n, so that for all m above n, the coordinates are equal, right? So maybe you start that here you have 0 and here you have 1, so they are different. Here you have 1 and here you have 0, but there will be a point after that they agree entirely, right? And the interesting thing is that, well, here I'm making various claims. The first claim I'm making, like the picture implies that this eventual equality is strictly above equality. This is not very difficult to see. In fact, depending on how much time I have, I may sketch it. Right. Right. But also the picture, in a sense, says that there is nothing in between. There is nothing in between. And the fact that there is nothing in between, it's called the Glimm-Epros dichotomy. Because what Glimm and Epros did is that they showed that if this is not, if this group is far from being abelian, so in technical terms, it's not abelian by finite. This is the technical term, but let's say if gamma is far from being abelian, it is above this point. You cannot it is either this point or above, right? So I guess Glimm and Epros showed that if Z is not is far from being abelian, then it cannot be completely classifiable. And much later in the work of Short, using the later developments in invariant descriptive set theory, Short showed that if the group is not close to being abelian, it's neither classifiable by countable structures. So you cannot use graphs, let's say, up to isomorphism. You cannot use graphs up to isomorphism as an oracle to classify unitary operators up to unitary equivalence. Sorry, irreducible representations up to unitary equivalence. Yeah. So this is and still we don't know this problem. This problem of classifying irreducible representations up to unitary equivalence, if gamma is complex, we don't know where it lands exactly, but it is above this cluster.
Can you give us some intuition for why the purple is more difficult than the green? Or the countable structure is more difficult than hyperfinite? Is there some intuition for that?
Let me be very vague.
They both just sound really difficult.
Let me be very vague, but be vague in a way that I'm trying to connect it back with the one we were talking about, the homology, right? So here's the heuristic: is that generally, look at this problem E0, right? Any point you give me in the Cantor space, look at its equivalence class. Its equivalence class, so everything that's eventually equal to this point, it becomes dense inside the Cantor space. So let's say you start with the Cantor space, and I hand you 2 points, right? And your goal is to decide whether they're equivalent, and you want to do that in a Borel way, right? Using Borel computations, right? Well, one thing you could hope is maybe you can find somewhere an open set where the orbit of this hits, but the orbit of this doesn't hit. If you do that, then you can say that they are not equivalent. However, because the orbit of this in eventual equality here, the orbit of this is dense, and the orbit of this is dense, they hit precisely the same open sets, all of them. So you cannot really use open sets to discriminate between 2 non-equivalent points. And what happens with graph isomorphism is that if you fix a complex enough graph, let's say, and if you look at inside the space of all graphs, you look at its orbit, like all other graphs that are isomorphic to it. This orbit not only is dense, but it is very entangled with other orbits in a way that it's even more difficult to separate. So what I want to this is like it could be like a semester of a class, could be an entire class to try to understand what happens here in terms of complexity. But roughly speaking, what you need to remember here is that the heuristic is that the more the E-classes become highly dense in the space and more wildly entangled with one another, the higher the problem is in the Borel hierarchy. Right. So now remember, let me see if it's the next slide. Right. Yeah. So now remember what happened with the dyadic integers mod Z. You had the copy of Z inside the integers. This was a dense subgroup. And of course, when you mod out, what you do is that you look at the coset equivalence relation. 2 points are equivalent if their differences in the same coset. So you can think of it algebraically as the dyadic integers mod Z, but you can also think of it from this perspective. You have the dyadic integers, which is the Cantor space essentially, modulo the coset equivalence relation, which has dense classes. So it ought to be up in the complexity. In fact, happens to be equivalent to hyperfinite, right? So dyadic integers mod Z as a classification problem is here. But so far I've presented you 2 pictures. The one picture cares about the algebra, but not about the Borel complexity. The other picture cares about the Borel complexity, but not about the algebra. And the project and what these talks are about is how to put these things together. Right. So how do we do that? Right. So the observation is that a lot of these theories in the first slide, like Stirner homology, Chekhov homology, X for countable abelian groups, and Lim1, all these come from cochain complexes or chain complexes, which is what we can call Polish cochain complexes. This means that these groups are not just abelian groups, but carry a natural Polish topology. So what's a Polish group? A Polish group is a topological group whose topology is Polish, meaning you can put a metric on the group which is compatible with the topology. and this metric is complete. And moreover, these groups are separable. Okay, so it's a separable topological group that can be metrized by a complete metric. Okay, so in all these examples, it turns out that that these groups can indeed be, carry a Polish topology, and the topology that makes these co-boundary maps continuous maps, right? And whenever you have a situation like this, and now we're getting into the main definition of this, the main object that we're studying, and for that, let me open a definition also here as I said. So this will be, so from now on, we'll not be caring about groups, but we'll care about groups with a Polish cover. And examples of groups with a Polish cover are homology or cohomology groups coming from Polish chain or cochain complexes, right? But okay, so let me point out here. So whenever you have a certain cochain complex, well, CN here is a Polish group. The kernel of this map is a pretty much of a point, the identity. The identity being a singleton, it's closed. So the primate of a closed set of the continuous map is a closed set. So the kernel is a closed subgroup of a Polish group. So it is Polish. This is the first bullet. Now the image may not be Polish in the topology there, but you can potentially put a stronger topology to make it Polish, and this topology you can read it off from where the map came, from the domain of the map. So this image is a group inside CN, but it came as an image of CN plus one that has a Polish topology. So maybe because this may be a little bit too cryptic, or maybe let me write it here because I think people can see from the Zoom here. So think of the reals modulo the rationals. Now the rationals, if you view them with the usual subspace topology, this is not a Polish space. It's a classic result in so often is given as an exercise in descriptive set theory, that if you have a countable dense subset of a Polish space, this cannot be a Polish. That does not have a Polish topology. Right? It's what we call this a sigma not the delta. So this topology here is not Q with the induced topology is not a Polish space. However, you can put a finer topology, which is the discrete topology, to make it Polish. So Q as a subset of the reals is not Polish, but it is polishable. You can put a stronger topology, and the catch here, the important thing is that it has the same Borel sets. So the discrete topology on the rationals and the interval topology on the rationals both induce the same Borel sets on the rationals, which is all sets that were in the rationals, right? But yeah, anyway, so this is a typical situation. So we'll take it as a definition, and even if we don't care about the homology and homology, we can study groups with a Polish cover for their own sake, right? So from now on, what's a group with a Polish cover? Is any Polish group G together with a polishable normal subgroup. When we do homology, G is always abelian, so normality is always there, right? So we don't care so much about it. So whenever we have a Polish group and we mod out by a polishable normal subgroup, this quotient, we'll call it a group with a Polish cover. And I'm thinking of it like this. I'm having G mod n, and I can lift things up here on G. So there is G that projects down on that. So constructions that I want to perform here, I can often lift them up here, and here I can use the Borel structure to discuss whether these constructions are definable or not. So here is the second part of this important definition, the definition that from now on we'll be working with. So let's say you have another group with a Polish cover, right? So this is the cover here in the prime. So now at this level, you may care only about homomorphism, group homomorphism. So let me give you an abstract group homomorphism, and I want to say whether this is definable or not. A group homomorphism will be definable if I can find the Borel leaf Meaning if I can find a map here, let me see, it is a hat. That makes the diagram commute, and F hat is a Borel map. So here's an important point. I'm not requiring F hat to be a group homomorphism. I'm only requiring it to be a Borel map. So algebra on the quotient, definability above, but not. So here you don't have definability and necessarily and algebra. And here you don't have algebra and definability necessarily together. Here you have algebra and here you have definability. So you have a group homomorphism that has a Borel map as a leaf. This Borel map is not, we don't require it to be a homomorphism. It's important that it's not. It's just a recipe, it's just a Borel recipe that tells you how you can think of this. Right, so not homomorphism in general. And okay, and similarly, you can find what the definable isomorphism is. It's what you expected. It's any isomorphism in the quotient that leads to a Borel map. Now, this map doesn't have to be injective, for example. The leaf doesn't have to be injective or subjective. It can be anything it wants, as long as it's Borel, and as long as it makes this diagram commute. Right? This is what a leaf means. Make the diagram commute. Yeah.
All right, so two things. One, so for this definable isomorphism, do we require that the inverse also be definable?
Great question. I'll address that either in the second talk or the third talk. We don't, but it's a theorem that it is.
Okay, great, thank you.
So the category. So we'll work from now on. We'll work in this category of group Polish cover, and there the categorical notion of isomorphism turns out to be this. And the reason is that whenever you have a definable isomorphism, meaning you have a Borel leaf, it turns out that the inverse is also a Borel leaf, but this you have to prove. Right.
And then also, is there a reason, should I be thinking about polishable as different from just thinking of it as a standard Borel space? Is there a reason?
Yeah. Yeah, because there are Borel subgroups. There are Borel subgroups of the Polish group which do not admit any Polish topology. One such group is that if you fix any let's say piecewise linear manifold and you look at the piecewise linear homeomorphisms, this is not a polishable group. It's a difficult theorem. I have more less interesting but more easy to prove examples of Borel groups which are not polishable. We can discuss later if you want. Yeah. But this assumption is not it's not trivial here, right? And I don't want to I will not finish the slide today. The slides today I will continue more. But let me finish with this slide. So okay. So the standard setup so far, how I have been taught algebraic topology, is you work. The objects are abelian groups, abstract abelian groups, and abstract homomorphisms are the maps, and isomorphisms are abstract group isomorphisms. Well, now we turn everything definable in this way. So now for map, in the definable setup, the category we look at consists of our objects are groups with a Polish cover. The maps are definable homomorphisms, and isomorphisms are definable isomorphisms. And the point now is that the definable setup is much more rigid. So we will see, for example, that while Steenrod homology cannot classify a certain collection of spaces, we'll see which collection. Definable homology can classify them. But what I want to do is to leave you with a homework, if I may. Right. So back to this example here. So this is something to think about. Okay, this is something to think about. I'll address it tomorrow. I'll discuss it tomorrow. But because this is an easy group, it's a group that all of us have encountered. It's also interesting because if you think about it, the way that we build usually sets that are not Lebesgue measurable is by choosing representatives from each class. So there is definitely some friction with definability here going on. Has to do with this density, right? But okay, look at this group with a Polish cover. So you look at the reals mod the rational, right? And now what I want you to think about, try to figure out how many abstract group isomorphisms. So think of this as a group to start with. So this is just a group. In the first bullet, it's just a group. And I think how many automorphisms, group automorphisms you can build, right? So these are isomorphisms from the group to itself. And now try to think how many of these admit a Borel lift, meaning you can describe them by by a Borel map. This Borel map doesn't have to be injective or surjective. It doesn't have to be Borel, and to make the diagram convenient, right? So I think it's a good time to end here. And what I want to say is that I'll answer these questions in the next talk, and we'll pick up from here and I'll give you some. The next talk will be a bit more technical because I want to address problems like that, which maps are definable. I'll remind you the definitions here, right? And then the third talk will be applications that back to algebraic topology, topological and homological algebra. I'll stop here.
Thank you.
We have time for a couple questions.
Yeah, if anyone has questions online, please feel free to unmute yourself and go ahead also.
Yeah, I'm just curious, the invariants might be finite, but they could also be harder to calculate.
Right, so that's why in the next talk I'll give, it's how you compute it, how do you calculate things? How do you, I give you two groups with a false cover, which may be isomorphic, but they may not be definably isomorphic. And how do you, what's the machinery you need for that? This will be covered in the next talk.
Does this form an abelian category? Like how much homology theory can we do in this setting?
That's a good question, and the precise answer. So there are many constructions that can be performed in abelian categories that you can do here. At this point, I don't remember if one of the collaborators here has proved that it's an abelian category, or you have to move to something slightly different, which we're going to discuss in the third talk. But let me remind myself what is the status right now question, and maybe I'll come back to you tomorrow.
Great, thank you.
Yeah, but many constructions, like for example, we'll see that things like the stake lemma, things like this can be performed here as well. Large constructions like homological algebra work for groups with a Polish cover.
Okay, last chance for anyone online to ask a question. Okay, thanks a lot.